Okay, so back in year 12, you already met the binomial expansion, which is used to expand algebraic brackets, which are raised to a particular power. And you were able to do that for any power that was positive and a whole number. The generalization was introduced to you like that, and then further like that, where that n1 bracket, n2 bracket was written as an expanded power of factorials. So hopefully this first example here is one that will just refresh your memory from your work in AS. So what you need to do is to compare the bracket that you've got with the standard expansion. So in this case, n is going to be 3, and the x term has to be all of that, so minus 2x. And then all we need to do is to substitute that into that expansion. So what we get is 1 plus nx, which is going to be 3 lots of negative 2x, plus nn minus 1, so 3, 2 over 2 factorial x squared minus 2x all squared, plus 3 times 2 times 1, n minus 1, n minus 2 over 3 factorial negative 2x cubed. And as you see, that will then terminate at that point. So we can simplify that further. 1. Here we're going to have 3 times negative 2, negative 6x. In this case, we have that negative becomes squared, so that's a positive. Everything else is positive, so that term is going to be a positive term. On top of that, we're going to have 2 squared is 4, times 6 is 24, over 2 factorial. Well, 2 factorial is 2 times 1, which is 2, 24 over 2, 12x squared. With this term, the 3 times 2 times 1 is 3 factorial, so that will cancel with the 3 factorial. Out of this cube, we're going to get a negative, minus times a minus times a minus, and then 2 cubed is 8x cubed. So that is a question that you would have been able to answer from your AS studies. Also at AS, you learned how to use that expansion for terms where inside the bracket you haven't got 1 plus, you may have 2 different things. And also, rather than having to use this expanding factorial each time, you would have discovered Pascal's triangle. So for the second example, we will use Pascal's triangle to speed things up because it's a relatively small power. So Pascal's triangle goes like this: 1, 1, 1, and then the next row would be the sum of the previous terms above it. So 1 and 1 is 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So these are the coefficients that we get from the factorial part of the expansion. And for to the power of 4, that's the power of 0 to the power of 1 squared cubed to the power of 4. So that's the row of the triangle that we need. So with this expansion, the coefficient is 1. Then we have the 2x part of it, and that's going to be to the power of 4. And then the plus 3 part of it will be to the power of 0. So that's going to be the first term, and you can see here that the 2 powers add up to 4. The next term will have the factorial part of it 4, 2x to the 3, and 3 to the 1. So again, they add up to 4. Next term will be 6, 2x, that goes down 1, that goes up 1, plus 4, 2x to the 1, 3 to the 3, and then the last term plus 1, 2x to the 0, 3 to the power of 4. So that's the expansion, which we can now tidy up a little bit. So 3 to the power of 0 is 1, anything to the power of 0 is 1. 2 to the power of 4 is 16. So the first term, 16x to the 4. The next term, we're going to have 4. Out of this, we're going to have 2 cubed, which is 8. Out of this one, 3 to the power of 1 is 3, x cubed. Next term, we'll have 6, 4, 9, x squared. Next term, 4, 2, 3 cubed is 27, x to the 1, sorry, not x cubed. And then the final term, x to the 0 is 1, so it'll have no x term, and 3 to the power of 4 is 81. So just to tidy that up completely, we'll have 4 times 8 times 3, which is 96 x cubed. 6 times 4 times 9 is 216 x squared. 4 times 2 times 27 is also 216 x plus 81. So that is your expansion of the bracket 2x plus 3 all to the power of 4. So again, that is something that I'm just refreshing your memory with. It's something that you would have dealt with at AS. So at AS, all the expansions that you would have dealt with would have had a positive integer power. Now we come to A2, we can extend that further for a power that's any real number, and that makes this particularly powerful. There are two conditions that you need to be aware of when dealing with powers that are real, and those are those 2 bullet points there. First of all, the series that you produce, as we'll see when we generate some, are infinite, so we expand them to a given number or an expected number of terms, and also they are only valid if the value of x being substituted in is between -1 and +1. Now we don't need to prove that at this level, but we'll take a look graphically at how that appears. Okay, so let's take a look at this first example. So Eg3. Expand 1 minus 3x to the -2/3. So comparing it to our standard expansion, 1 plus x to the n, we've got to let x be -3x and n is -2/3. And what the question wants us to do is to expand this up to and including the term containing x cubed. Okay, so 1 minus 3x to the -2/3 is going to be 1 plus nx minus 2/3 times x, which is negative 3x, plus n times n minus 1. So n is minus 2/3. Minus 2/3 minus 1 is minus 1 and 2/3, which is minus 5/3 minus 3x squared all over 2 factorial. So you can see now why this is going to be an infinite expansion, whereas with the AS examples you end up with that ending up at 1. With this, these coefficients are going to get increasingly large or small. So we're going to take, to get the x cubed term, that's giving us the x squared. We now have to take another 1 off, which is going to be minus 8/3 negative 3x cubed all over 3 factorial. And then that continues as a sequence, but we stop there. Right, let's do some tidying up here. 1, this term is going to be positive because we've got a minus times a minus. On top we get 6 over 3 is 2x. With this term, those two will produce a positive, that square will produce a positive, so it's plus again. On the top of this we have 10 times 3 squared is 9, 90. On the denominator we have 3 3s and 9, 2 factorial is 2, it's going to be over 18 x squared. Deal with the sign now for this term. So we have minus times a minus times a minus is negative. That cube is going to give us a negative. So negative times negative, we'll end up with a plus again. On the top of this one, we're going to have 10 times 8 is 80. And in there, 3 cubed is 27. And on the bottom, we can have 3 times 3 times 3, which is 27, times 3 factorial, 3 times 2 times 1 is 6 x cubed. 1 plus 2x, 90 over 18 is 5x squared. I have worked those out previously, but just to keep the video relatively short, I'm just giving you the answer. Similarly with this one, the 27's cancel, and 80 over 6 is the same as 40 over 3 x cubed. So that's my expansion up to and including the x cubed term. State the set of values for which the expansion is valid. Well, that is when the modulus of x is less than 1, but my x is this negative 3x. So I have to say valid for modulus of 3x is less than 1. Now, dealing with that, what the modulus does is force that to be positive, but if you want to think about that as what that's saying is negative 3x must be between negative 1 and plus 1, and we want to get the x on its own. So if we divide throughout by negative 3, then we get 1/3 x negative 1/3. And from your GCSE studies, you should remember that if you multiply or divide by a negative number, it flips the inequality. So what you end up with is that, which means x is between 1/3 and negative 1/3, or modulus of x is less than 1/3. It means the same thing. If you're happy going from there directly to there, don't worry about that inequality form. So this is only valid for values of x between positive and negative a third. Using GeoGebra or a similar graph plotting software, consider the validity of the restrictions on x. Now, again, I've sped things up here by already entering those functions onto GeoGebra. The green function that you can see there, which is the one with the asymptote, is 1 minus 3x to the negative 2/3, and the red curve is the binomial approximation that we've got. And what you can see there is if you put in a value of, say, x is minus 3, there's an enormous difference between the y, or the output, on the green curve compared to the red. But between there and maybe there is a really close similarity to the two. So the modulus x is less than 1, as I said, isn't something we can prove at A level. However, we can see graphically that that case is valid. And then part D, calculate the relative error between the actual function and its approximation when x is 0.1. So what we do for that is if we sub 0.1 into the original function, and work out what that is. Now, if you have a scientific calculator like this, I can just get the light to shine helpfully. It isn't doing that at all. That's better. Then what I suggest you do is use the memory functions to assign 0.1 to a variable. So if I type in 0.1, shift that one to store, and then I'll put that in x, which is alpha open bracket. That didn't work. 0.1 store in x, so you don't need to put the alpha in. Then I can now just type that as open bracket 1 minus x, 3x, close bracket, to the power of minus 2/3, close bracket. So I've typed it exactly as I see it. So that's going to be 1.2684 blah 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 blah, and I'm going to store that in its own variable a. So rather than have to write that completely accurately, I've stored that in a. Now I've got to put that into my expansion. So 1 plus 2 lots of 0.1 and on this x has still got the 0.1 in, so I can just put 1 plus 2 alpha x plus 5 alpha x squared plus 40 alpha x cubed over 3. So again, just typing it in exactly as I see it. And that works out to be 1.26 3 recurring, and I'm going to store that in B. So shift store B. So the relative error is going to be the difference between the actual answer and its approximation. So A minus B divided by what it should be, which is A, and then times 100 to turn it into a percentage. And because I've stored those values into those variables on the calculator, I can just type that now exactly as I see it. So alpha A minus alpha B over alpha A times 100. So the relative error is 0.4%. And my mobile will hopefully shut up in a moment. So the error between the actual answer for x equals 0.1 and our approximation with ascending powers of x to x cubed is only, or is less than 0.5%. So pretty accurate depending on what we need it for. So that's Eg3. Unlike when dealing with n as a positive integer, if n is real, it's not straightforward to expand expressions like a plus b to the n in the way that we did in the second example there. So there's a bit of work to do, a bit of rearranging before we use the expansion. So that's what Eg4 looks at. So expand 1 over 4 minus x in ascending powers of x up to and including the term in x cubed. So the same thing as we did previously. So let's see how to do that. And stating the set of values for which it is valid. So first of all, let's write it in index form. So 1 over the square root is the same as writing to the power of negative half. Now we need that to be 1, so we have to take that out as a common factor and write the inside as that. So just to make sure you're comfortable with that, if we multiply that back out, we get 4 times 1, which is 4, and 4 times that, the 4's will cancel, giving you the minus x. And that's all to the power of minus a half. We can bring that power in because we have a product in there, so that is the same as 4 to the power of minus a half times. So that is now something that we can apply the expansion to, and this we can simplify. 4 to the minus a half is the same as 1 over the square root of 4. Which is the same as a half. So this now is something that we can apply a binomial expansion to, and what we're going to do is let x equal or represent minus x over 4, and n is minus a half. So my expansion is going to be a half, and then 1 plus n x plus n minus 1 is minus 1.5, which is minus 3 over 2, minus x over 4 squared. And you have to remember that there's the 2 factorial in there as well, which is an easy mistake or an easy thing to leave out. And then to get to the cubic term, we get to take another one off. Then we have the x over 4 cubed and the 3 factorial. So let's start to tidy that up. 1. From this term I get a plus x over 8. From this term I get plus times plus is plus. On the top I've got 3. On the bottom I got 4, 16. 2 factorial is 2 x squared. And from the cubic term, negative, multiplying those, negative from that, it's going to be positive again. On top, I've got 15. On the denominator, 2 times 2 times 2 is 8. 4 cubed is 64. And 3 factorial is 6 x cubed. I got the half outside the bracket still. This simplifies to 3 over 128 x squared. This simplifies to 5 over 1024 x cubed. Multiplying in the half, I get a half plus x over 16 plus 3 over 256 x squared plus 5 over 2048 x cubed. So that's my binomial expansion of 1 over the square root of 4 minus x, and it's valid for, and the restriction is on this. So the modulus, that has to be less than 1. So I'll do it the long way, just in case you're not comfortable just working with the modulus. So I'm going to multiply throughout by negative 4. So that becomes plus 4, inequality changes, x, which is the same as saying x is between plus 4 and negative 4, or modulus of x is less than 4. And again, you can plot that on GeoGebra and see that the graph of that and the graph of that are pretty close together between those values. The final example that we need to look at is just to show you what happens if you end up having to combine 2 expansions. And when you're combining 2 expansions and the validity, you're looking at what values of x the whole expansion is valid for, you need to consider the stricter of the 2 regions of validity. So we'll take a look at that. So we are finding the first 3 terms in the binomial expansion of 3 over 1 minus x, 1 plus 2x. Okay, well we need to write that in index form. So we can write that as 3 1 minus x to the minus 1 multiplied by 1 plus 2x to the minus 1. So if we take this first expansion, then x is going to be minus x, and n is going to be minus 1. First term, second term, third term, minus 1, minus 2, minus x all squared over 2 factorial. And the question wasn't asking us to go to the x cubed term, it wanted the first 3 terms, first, second, third. So we don't need to go any further. So that's going to be 1 plus x, and then out of here becomes plus, that's 2 factorial, we'll cancel with that. So we just get x squared. And that's valid for the modulus of minus x is less than 1, which means, so that part of the expansion holds true for any value of x between -1 and 1. Now we consider the second expansion. So for this one, the x part is actually 2x, and n is -1 again. So this time we get 1 plus -1 2x plus -1 -2 2x squared over 2 factorial. 1 minus 2x. Again, those factorials will cancel, so I get 4x squared out of that one. This one is valid for modulus of 2x is less than 1. Well, that's the same as that, because the 2 is just positive anyway, which is the same as that. So I haven't gone through the between -1 and +1, I've just dealt with the modulus, but you can do it in exactly the same way as in the previous examples. That's just more efficient. Okay, so now we need to build the whole expansion. So therefore 3 1 minus x to the -1 is going to be 3 lots of 1 plus x squared multiplied by 1 minus 2x plus 4x squared. But if we expand the 3 into the first term, I get 3 plus 3x plus 3x squared. And now I have to multiply that term by all of that term by all of that, and that term by all of that. But I only need the terms that are going to contribute to whole number x to the power of 1 or x squared. Any higher powers I don't need to worry about. So the first one is going to be 3 minus 6x plus 12x squared. Second one, 3x plus 6x squared, and then I don't need to worry about the next term because it would be cubic. So if I just put in there plus etc etc etc, and then from this one, the first one is going to give me a squared, so it'll be plus 3x squared. But again, from then on I'm going to get a cubic and to the power of 4. I don't need to worry about those. They're not going to be in my first 3 terms. Tidy it up. 3 negative 6x plus 3x takes me to negative 3x. And then x squared, I've got a 12. That there should be minus 6x squared, shouldn't it? So 12x squared minus 6x squared is 6x squared, plus 3x squared is plus 9x squared. So that's my expansion. Now the values of x need to meet both restrictions. So the first restriction is that x must be between -1 and +1, and x must be between -0.5 and +0.5. So for that to be true, x can't be 0.7, for example, because it meets that condition but not that. So in order to meet both conditions, the strictest of these two have to apply. So 0.4, for example, satisfies that condition and that condition. 0.6 doesn't, it doesn't meet that. Okay, so hopefully those examples will now help you work your way through exercise 7A.